Okay, so now let us look at various libraries that implements this RS code and other erasure coding applications. So J erasure library is one of the things. It has a C library facilitating erasure coding. So we will go through some of these material with some demo, so that some information will be given. You could probably download this and try out these finite fields and the issues happening that I mentioned. So what needs to be understood in this kind of thing is that not always all functionality of finite fields are used in many erasure coding applications. So mostly XOR and simple operations. That requires also knowledge of the MDS applications, and so to that extent they are related. But as we are moving towards the more distributed storage, I think now implementing finite field is not a big concern, and that is why I specifically took care to give two set of slides for finite field, understanding how elements are implemented, to going through with simple example, and similar issues will come in practice as well. So how J erasure library implements it? This is a you can download, you can do it yourself. That way you can appreciate some of the issues going on with that. Okay. So in this lecture we will be looking at the library and its routines. What are the things possible? So far whatever this thing in example encoding and decoding of popular codes that have been discussed. Then analysis of CPU performance for various codes, we will discuss about that, and Aaron will show some when we are switching between the demo mode and talking, and so we will so you will have to probably bear with some with some things will happen, okay, and we will probably exchange these ones, and so we won't okay. So what is this library, J erasure library? It is downloaded from this web address, and it is written in C++ and uses GF complete, a comprehensive library for Galois field arithmetic. So I mentioned about the interesting in Galois field. The GF complete actually does it. So this has implements Galois field in very efficient ways by using sometimes arrays and optimizing it for various processors, etc. So it's very difficult to beat the timings that this GF complete tells. So it has a procedure for GF arithmetic for from 1 to W up to 32. So it can implement easily 1 to GF2 to the power of 1, GF2 which is binary, GF2 square, GF2 cube, GF up to GF32. Addition subtractions are simple XOR now. So you can see what type of representation he would have followed. Simply the polynomial representation, just XOR. Division and multiplications are more complex, requiring many operations in order to compute results, and sometimes they are all managed by large arrays. Okay, so there are very interesting ways you could do, and there is a that's the study of how to efficiently implement finite field is a very well studied topic. Okay, when if for example each new processor comes into the market, each digital signal processor comes into market, people come up with their own innovative way of actually implementing. So most of the computers come with 8-bit or 16-bit or 32-bit registers and memories, so it makes sense to work under those conditions. But if you there is no restriction. So in fact, for example, finite fields of order GF31 can be as efficiently implemented as 32. So as long as you are within the word boundary, you could do better. And then if you want to express higher order finite fields, then you have to do a lot of data structure innovations. That means sometimes it is used in array, sometimes it is in linked list, or all this is based on this kind of thing. So when we were in the company in Bangalore, we also implemented in our own way with C language and with using some arrays, and arrays we used only 256 arrays, but we could just manage many things, and that requires so there are ways you can do. So if you have an array of higher size available, it may be much faster, but if you have higher size array, then there is the speed really depends on whether the array is loaded in the main memory. if the array had to be fetched down each time from the disk, then you won't get the advantage. So you'll have to do a lot of tricks in making it work well, but GF complete does it in that way, and these kind of things. This is the first one. Some are pre-computed and stored in lookup tables, and Amata is the constant time. With respect to Hadoop, we just introduced Hadoop briefly in our previous thing, but I think we will do a bit more on Hadoop day after tomorrow. That time this was heavily based on JArray. So initial Hadoop 2 was heavily based on JArray library. The library was last updated in 2014, and after that it's not supported anymore. So it's not going to be supported. So any issues you download, it's your headache to do it. So in some sense it is best to understand that way. You can do whatever way with it. The latest version of the Hadoop actually uses Hadoop. This is 3 alpha. It's in May 17. This erasure code module in the latest Hadoop uses a Java coder developed from scratch. So they did from Java, from the scratch they did in-house, and that is faster than HDFS write. So it comes with a lot of optimizations for name node overhead. So I mean, other than that's nothing to do with the finite field. It's to do with the distributed system, but it incorporates Intel storage accelerator library to accelerate encoding decoding. So obviously many of these things, the accelerator library will come, so that can be used to implement the thing. Yeah. So the similar thing, when we discuss about finite field, I think as far as this course is concerned, like exactly how to use the Intel accelerator library and other things will be more technical. But on the other hand, if you are able to actually understand the finite fields or the simple examples very clearly, and the issues in both the vector representation or the exponentiation representation, if you understand, that will be a lot, and that will be useful to actually even understand what these people do, and then you can write over above it. So at this point of time now I'll give it to Aaron.
So I'm just going to talk a little bit about software. Obviously it's something that you can download and try out on your own computer if you haven't done so already. Who here programs in C or C++? Anyone? Most of you, indeed. Good, that's good. What about, do you use Linux? Who's got Linux on their laptop? Most of you? Well, that's good too. That's great, actually. So you will be able to find this software, and basically it follows a free software foundation type format. It's make files, autoconf, this kind of thing when you download it from a JIT repository. In fact, let me just quickly go. I got it on a web page here. This is the JIT repository where you can go. If you Google for it, you'll find it very easy. This is the JErasure package. This requires GF Complete to already be installed, right? So you'll sort of have to go to GF Complete first. I'll tell you a little bit about that in a minute. To install that, and then you go and you get JErasure. You can clone it and compile it. And in fact, Udaya was saying it's maybe not being used much. I see 3 months ago that people have looked like they've merged some things in and so on. So that's not too bad. That 3 months ago sort of means that maybe people are reviving it a little bit or something like that. So there might be a bit of a community there around using JErasure. And indeed, if you're nice with open source, you can contribute as well along the way, perhaps. This is the sort of thing that you like to contribute to. I'm sure that people would, welcome some sort of contributions to the open source. So you could go there and have a look. I'll just go back to the slides. It's a bit flaky. If you're using Ubuntu 16, which probably all of you would be doing if you're using Linux, then the GF Complete, luckily enough, you can just do a sudo apt-get and it's package managed. You can just install it that way, and that's very convenient. But with the JErasure, as I said, you'll have to go there and download it or clone the instructions are here on the slide. Indeed, clone the JIT repository, go through the auto reconf, which will construct the make files for you, and then the configure and then make install, and it will put everything into your install everything for you, what we've installed on this computer, and you'll have the same example code and all of that we're going to run now. That's with Ubuntu 16. If you happen to have it a little bit older, you'll need to install GF Complete first because that's not package managed on that one, and then do J erasure. There are some issues. You might have to fix some things here and there because it probably the community is small and they're trying to keep up to date. But if you have any problems, so like if you try to compile it while we're here, I can sit down with you and we can sort of work through some of that. If it doesn't work for you, somehow we get it installed and running on your laptop. But it should be pretty straightforward, I think. So just before we get to the demos, we'll let Udaya talk a little bit more about what we're going to do.
Okay, so here in the basic assumptions we do is here k devices, as usual in the MDS things, k devices hold data and m devices whose contents will be calculated from the original k devices. So encoding takes original k data devices and calculates m coding devices for them. So with J erasure it uses the word called W, and that's it called as a device. So each such that's signal W that tells you a device, and if you have a big file, it's just simply repeating the same steps for a bigger file. So decoding takes again k power m devices with erasure and recalculates the contents with the original size. So W is called the word size and it is set to either 8, 16 or 32 depending on this J erasure allows you to set these words, and that as in the things. So say for example W is 8, the first byte of each coding device will be encoded with the first byte of each data device, second byte of the coding device will be encoded with the second, and so forth. This is what the stripe things I added. So if you have k devices and m devices, all first bytes will participate in the first thing, and then every W by W the whole data is computed. So that's how we do. So I mean just to bring back the ideas that we mentioned, some codes don't operate on the entire bytes. They want coding bits Cij to be bitwise XOR of some subset of other bits. So depending on the even odd code, when we do that, there is a special way to tell you where the the checksum is computed. So to cater such cases, each device is assumed to be composed of W packets of equal size. So we have the previous slide. So we have W is set to 8. So this is set to 8 now. That is fixed. But then when we use some codes don't operate on the entire byte. So in that case you will have a W packets of equal size. For example, with k equal to 4, m equal to 2. So W is equal to 4. Okay, here. So this W packets will be used. So each code word is calculated corresponding to the things. For example, C10, this one is computed as a D00, D11, D22 and D23, and that XOR will go there. So this is how, it's just an example. The size of each packet is called packet size. So the coding system is represented as a distributed matrix using a matrix vector product. It is basically generator matrix represented in a way that is easy to visualize the disks also other than. So for example, when we have a generator matrix, we have our own vector and we look at the symbols, but here it is for example here, so this is same generator matrix. I have put an identity matrix here. You have data up to k minus 1, that this actually k data. And all the parity calculations will be in the distributed matrix. So if you multiply by this data, see D0 is picked up and that goes into this, D1 is. So you can see that whatever I wrote in the other slide, this will be in the transpose of it, and that's how this J erasure library you do it. So one of the objectives of studying coding theory and looking at this is basically here we make a mathematical theory, understand how generator and code works, and then when another public library like J erasure, they need not follow the same thing. They might do it in a complementary manner. So we should be able to figure it out the relationship. Okay. So is that clear? This one. This is actually we did not want to change this. This is from the technical report by Planck and Greenen. So, most of the figures, it is a very excellent resource that help you to understand this. So, encoding and decoding, the matrix is multiplied by a data vector encoding, which gives a vector containing both data and code words. So, during decoding, a decoding matrix is created from k rows of the distribution that correspond to the non-failed devices. So, we invert this matrix and multiply it by both sides of the equation to obtain decoding equation. So, the inverted matrix multiplied by the survivors equal to the original data. So, a very simple idea is used. So, J erasure 5 basically takes 5 parameters. It takes k, m and w and the size and an integer seed to a random number generator, performs a basic Reed-Solomon coding, and k plus m must be less than or equal to 2 to the power of w. Size is the total number of bytes in each device, must be multiple of size long. Okay. So, for example, is you have a J erasure 0 5 and then it give you all this k m, w is 8 bit, k m is 2, w is 8 bit, size is 8 bits, 8 bytes and 12 is the integer just for creating a random seed for that. So, this creates k devices each with size of bytes of random data and encodes them into m coding devices. So, erases m random devices from the collection of data and coding devices and performs the decode, prints the decode matrix with first m devices array. So, if you run this one, you will get that idea. Yeah. See, you want to take? Second.
I just copied the command there as well. You want to explain?
So, when the coding is complete, the data is given in because that is the size, right, it's byte is 8. So, D0, D1, D2, D3, these are the data matrices, these are the coding matrices. So, it is in the same way, D0 it goes like this, D1 goes like this and so forth. So, now you erase 2 random devices. So, what are the devices we erased? D3, so it does not mention which one, but D0 and D3, does it mention there? So, yes, it is good. They are all zeros here, they are erased, and so state of the system after decoding it actually, for example, here see it restores to the value there. Suppose we have the first 2 devices, here is a decoding matrix that is used, and it is because it is a. So, next one is Reed-Solomon 1. This takes 4 parameters again, k, m, w and an integer seed for random generation. The classic Reed-Solomon coding of k devices into m using a van der Monde based distribution matrix. So, each device is up to store a size long, and the example like this. So, 2 which is k is in this case is 2 and then the m is 4, 8 and 103 is random, creates k data devices of each of size long and random data and encodes them to m coding devices and prints a coding matrix. So, of course, you could also do the erasure. So, you can see that it tells you about the m rows of a generator matrix. So, there are 2 coding, basically it has 2 data symbols and 4 different coding operations. Okay. So, first one is 1 D0 times D0 plus D1. So, this will be just C0 will be simple XOR of these 2. Is it true? Yeah, you can see that. You see 4, then A3. Can you add? A is maybe 10, right?
Yeah.
A is 10 and you can add 3 to it. So, it is you will one of them will go with because 3, 1 will add. So, that will be 9. So, 8 plus 1 9. So, you can see that this is the XOR of these 2. This is also XOR of these 2. 7 plus 2 is 5, correct, and A plus 1 is B. It goes to the next. Yeah. A is 1 0 1 0 and you add 1, so that's B. Yeah? So you can see that this one is exclusive out of that, and then this will be multiplication. 70 is some finite field element GF2 power 8 in this case, and that gets multiplied in that way and you get the 4 equations. So you now erase 4 random devices you erase, and you can by any 2 will be enough to recover the back thing. So Reed-Solomon 1 takes there. So now Reed-Solomon 3 performs RAID 6 encoding. This takes about 3 parameters k, w. So when it is RAID 6, all the parameters are fixed. So there are some specialized functions mainly for RAID 6. For Reed-Solomon, the general Reed-Solomon code, you will be able to specify k, n, and get whatever data you want. But for RAID 6 coding, the k is fixed, kw, and so the number of, I think m is anyway 2, so you don't need to specify it. M is 2. That's the random seed to just to start the, or it's just to to make the coding matrix to generate a data symbol. So it starts with some random seed.
So it picked 2 random drives to erase. If I change the seed,
yeah,
you'll see it's picked 2 different ones.
Something like that from 200.
No, it's a random number to choose. For example, let's say you want to fail 2 nodes, right?
The question is about what is the seed?
Yeah.
The seed is really just starting the random number generator. You use some randomness in this program, but if we put the same seed in, you'll always get the same outcome for that seed. If I change the seed, I'll get a different random process. It will always, if I use the same seed, I'll always get the same process, right? So it's a pseudo-random number generator. It's not really random. So it starts somewhere. So 103 will always give me this outcome. If I run the program again, I get exactly the same outcome. But if I put 104, which is a different seed, it will give me some other outcome.
Yeah.
It just enables me to reproduce the same outcome every time if I put the seed value there. That's what it's doing.
Because they're playing around with some random data, not any specific data. So that's why you need some seed to make it different. You can try that. We showed that here. Okay.
Without putting it, you can have the computer seed itself. Every time you run it, you'll get a different outcome, and you won't be able to go back to the redo the previous one because you didn't know what the seed was for the previous row. So this encoder takes a input file from the user and takes 7 parameters: input file, k, m, code to use, and w, packet size, and buffer size. Because at the moment now the file you can specify, because in the past it's some random data that is done within the program. Now you can specify a file for encoding. A buffer size represents the approximate size of the data in bytes to be read at a time. So this also kind of mimic, for example, why this is important to see is that when data is kept in a distributed storage, sometimes a node downloads it, you won't get everything in one go. So maybe the system fetches it by chunk. Okay, so we do so just to kind of simulate that this is just a library which we do, and this is a user functions given. So buffer size represents an approximate size of the data to be read at a time. So an example would be a test file, that this is the file to be encoded. K is 10, m is 4. So this is the parameters used for Facebook case, but you can try that. Then Reed-Solomon van der Monde matrix. Then there is it will be 8 and 1024, which is basically w is 8 and packet size is 1024, buffer size is about 50,000 bytes. Yeah. So data and coded blocks are stored in directory coding, and you can delete m blocks and perform decoder. You could do the decoder and you can compare the original and decoded file. So you can the decoded files, you can go there, corrupt something, and you can recover it. We've got a couple of files, one is 10 times bigger than the other. It's just the first one replicated actually 10 times over. So we'll go to this command here. It's actually missing a little bit there. So that should be 50,000. the buffer size is, you know, as you read, a bigger buffer, maybe you read more at once. And I will encode file 4. So it gives us some basic idea of how quickly it was doing that. This computer has a solid state drive in it, so it's actually quite fast. You can see if this is a regular hard drive, it might not be greater than like 20, 30 megabytes per second or something like that. So the files that then end up in coding, coding. Actually, I'll give it a bit more. You can see the
on the
K data and then the N file.
yeah. Yeah. So each for data corresponding to each disk is stored under K01, K02 up to K010. These are the file information buffer size, and then these are the 4 parity, and this has some metadata that tells you about where the bytes are there.
Which is about 10 times bigger than or something than what the original file.
Yeah, original file size is.
So what, we can remove some of these now and decode it and get back, right?
Yeah.
So in principle. So I'll just remove, which one is file for K05? How many can I remove?
You can remove, yeah, just a good question. How many we can remove?
4 of them?
4?
I can remove any 4 of them, right?
Yeah.
So I should have just picked all the M files. So is that 4? I removed 4 of them. Whoops.
You had to go to.
I typed something wrong, right?
M04 twice.
Where was it? File.
M04 has been typed.
M04? Yeah.
Twice.
Oh, I did it twice. Sorry, yeah, alright. So let's do another one. Let's just get rid of that. Let's do M01.
Yeah.
So they're all gone. And then supposedly if we run the decoder, I give it the same file name, file for text. So it goes away, it does some reading, and then inside coding it's got the original file, and I can kind of diff that with file 4 just to see are they the same. If they were different, then you know, it would tell me the differences, right? It would say no, there's a difference. So it says nothing, so it means these 2 files are the same. Now you could say, oh, hang on, it's cheating, it's just reading the original file or something like that. But no, I mean, you can look in the source code. I won't go there now, but I mean, all of these little example programs, there's many more example programs, and you can see the source code. And the source code is just, you know, generating a matrix, or, you know, reading from a file and putting things into a directory and that kind of thing. So that will give you a good idea how to use the library to build your own tools or whatever you want to do from using this library. I'll just run the program, and we'll code something a bit bigger. So I'll just remove that directory, and so let's see. So file 5 was 10 times bigger. Take 10 times as long, but it didn't take very long for file 4. And you know, it'll have different sorts of read speeds, decoding speeds, and then we can, you know, you can sort of, so actually, so that was decoding up there at 262. If we sort of go back a little bit, we saw, you know, the smaller file was 154 megabytes per second. Down here, we sort of got around the same. What happens if I maybe try the buffer size 10 times bigger, you know, to encode that file? Will it get any faster or more? Now we're sort of getting a much better read speed out of it. That's pretty good, you know, encoding speed for this kind of system, right? So the buffer size kind of gives you an efficiency. You know, you don't want to be constantly reading, but if you make it too too big, then you need a lot more memory to read everything in at once. If the file was very big, obviously you couldn't, put everything in. So these kind of things you can play with the tools. These examples, and as I said, you can really learn how JErasure works and the library works, and build your own kinds of storage systems even in D right on top of that. So
now think of this: if these are they're distributed, then there will be other issues, much more issues in terms of in terms of fetching this data and so forth. So so really when applying this Reed-Solomon coding to actually storage, we need that aspect as well. That is the bandwidth and the context in which they are done. Because sometimes you can fetch data faster, like with a bigger buffer, then you can probably manage the computations in a much better way. So all that, I think JErasure library, he optimizes it. But of course, if you want to use this in an actual system, there may be further issues. But what Aaron mentioned to you is actually this gives you an option to study them.